Thank you, Kyle. Yeah, after this talk, I want to take you back into a completely different region. As Kyle said, I'm product specialist on the life science side, so I'm a mostly LC person working with Orbitrap instruments. But what I want to show will work that way, basically with all instrumentation from Thermo. But of course, high resolution is the major background for it, and really the full power of high resolution makes this really a good solution. So I want to go into the range of screening. I think about quantification, lots of things have been said in these 2 days already. And I want to go into screening and show you what we can do in terms of screening, how far we can get on that side. So of course you start off with a sample and then you can decide where you want to go. What's normally done for such an analysis, or what I normally do if I'm asked to do something like that is, because I don't know very much about the sample in most cases, I just run a generic method. So in terms of LC spoken, that will be a 15-minute gradient, water acetonitrile. And as long as my sample is somehow liquid, has been extracted, or is an environmental sample or whatever, I just inject it, run it on a full scan fragmentation method. So we have a couple of methods present. But when we want to go to screening, we are down basically to 2 different methods. And the basic method will be run a full scan and run an all-ion fragmentation. Because when you run the sample, you don't know what you can get out. You basically don't know what you want to get out, if it really comes to terms. The second method you could run, but I don't want to focus too much on that. I want to go into the software. There would be a little bit more facilitated AIF scanning, which you call data independent acquisition, DIA. But to go to the software. So we want to do either target analysis or unknown screening, so a general unknown screening. And I want to go to the target at first, leave out the quantitation, just go into the screening directly. And that's what we use for that is the software called TraceFinder. TraceFinder can do both of that. So the whole workflow starts in TraceFinder, ends in TraceFinder. We'll see in between we will use Sieve for unknown screening as well. Okay, so what is the basis we are running on? We have somehow data, and if you look at that trace, it already looks quite meaningful. In many cases, it's even worse. You just see a baseline at 1E8 or 1E9 counts because you have some background which is just constantly in there. You don't see anything. This button here, okay. So there is a possible contaminant. How do you get there? Basically, what we apply is a targeted list. And the difference between classical targeted approach and what I would call a suspect approach would only be the size of that list. So if I know what to do, the classical analysis where I'm asked to do a certain qualified analysis will be, I don't know, 30, 50, 80 components to look for. A suspect screen, that could be that I just apply a list of 3,000, 5,000 components, whatever. Anyways, I have made up my mind somehow to a list. I apply that list, and I will get such an extracted ion chromatogram for one of these members there. And so because we have the M over Z, which is accurate and high resolved, and we have a retention time in most cases, that will put a name onto that, because we run a list where this retention time and the M over Z has been laid back down. So that gives us a name. But of course, that's not the point where to go. That's quite easy and is done for a long time. So the basic thing is, what can you do with it? So the first thing, of course, if you run full scan is that you have an isotopic pattern. And in TraceFinder is organized that way that we don't deal with masses as the starting point anymore. We are dealing with elemental compositions. And TraceFinder will calculate the masses from it, which makes it very easy to screen for every adduct you can think of, because the software does it for you. Just say, okay, screen for ammonium adducts, screen for sodium adducts. And TraceFinder just will calculate that. And you can do them all together. So an elemental composition is in the background. So it's not a big step to say, okay, we have the elemental composition, so we simulate the isotopic pattern, and then we do a match of it. And this comes for free in full-scan analysis because the isotopic pattern is always present. So that's the first thing we can do. We can run the isotopic pattern match, which is the first point of confirmation in this point. And then I said, the method run here will be, as a starting point, a full-scan AIF method. So we run the all-ion fragmentation. So we have a basically rather crude but existent fragment spectrum. And what the database can contain as well, and if you look in the trace finder as it is shipped at the moment, you will get a database of 1,000 components for environmental analysis and another 500 components for toxicology, pharmacology samples. So we have roughly at the moment a database of 1,500 components consisting of roughly 9,000 hydrosols spectra. And the according fragment masses drawn out of that. So we can run a library search with the library spectra which are present, and we can run a fragment search. So out of this fragmentation data, we get the isotopic pattern match, we get the library and fragment match. So you have 3 points of confirmation besides the accurate mass and the retention time to tell us if we are pointing into the right direction or not. Of course, all these things never can give the full answer without a qualified standard in the background. But at least this gives you a very good hint already. If you're not running standards for all the components, for the suspect screen, you never can run all the qualified standards. You cannot run 5,000 standards just for trial. But that gives you a very nice confirmation inside the software. The review later on will look like that. So you get lots of colorful dots. In this case, you see green and red ones. We have yellow there as well. What does it stand for? So we have basically the occurrence of a peak. I mean, without that green dot, it wouldn't occur here at all. So because the extracted ion chromatogram shows a peak. Second is the isotope, the ion ratio of the fragments we can take into account. We can take into account the isotopic pattern match. We can take into account the library screen and the fragment ion result. So in the end, we get 1, 2, 3, 4 identification points here, or identification patterns. The overall result you will see here, so the ones being green everywhere, look like that. Ones where 1 or 2 items are missing will look like yellow, and if something's not found at all, you will see it in red. So how can you review this data here? This is just an example. In TraceFinder software, the windows are highly flexible. You can move them around as you like, and here, especially this pane down here, contains lots of options, and I just took 3. Of course, you have a main quant ion. I mean, what we are running here in the latest version, we're running all on one surface. So this is the window we use for quantification as well. So the software is still saying quant peak, although we are not quantifying. The difference between such a screening and a quantitation is only if you run a dilution series of standards and qualify them as calibration standards or not. If you don't have quantitation standards, it's a screening. If you have quantitation standards, it will be a quantification, and you will get even a content number somewhere in the back of the table as well. Here it's run as a screening, so we have the main identification peak, and then we get the fragment ions, which has been observed in the background. You can see the ion overlay, so you immediately can see if the fragments are really co-eluding or not. There's a difference to the earlier versions where you just got the notification, okay, fragment ion is there or not. But looking into it in detail showed in many cases that this fragment ion was just background, just constant, and it didn't elude together with the main peak, and of course it has to. So here we have this ion overlay to make sure the fragment ions are present and they show the same elution pattern as the main ion. Then you can look at the isotopic pattern match here. You could look at the library score here, or whatever you have as identification item here, you can make visible here, as it is good for you, as you need it in that case. And in the end, you will get a report out of it. I don't show that here. Time is not enough for that. But we have a very nice reporting package, which is completely newly designed, where it's quite easy for you even to design a new report to get to the data you want to see. As you like, as an Excel sheet, which you can put on into LIMS, or as a PDF form you just can print out and store, sign and store, whatever you need. Another point here is that even without Cal standards, you can go into a so-called comparative view. This is just the part of it. So just think in your mind that on this pane, out of a sudden this here occurs. These can be on one line as many as you want. You can have as many lines as you want. But here I have an example of 2. You just can see the example in the background here are samples from a wastewater treatment plant. So this is the intake of the wastewater treatment plant. This is the first part, the biological cleanup. This waste treatment plant is equipped with an ozonation step. Following that, so you can see the first cleanup step, the second, and here we have a blank, still as a control. And here you can see for carbamazepine, for example, you see it's going in, but literally nothing is coming out. It's really red marked because the ion ratio doesn't fit anymore. It's more or less not detected. But here for another one, metoprolol, for example, you see, okay, the cleanup efficiency is not perfect. It's around 80% because you see this is the 100% peak. And after the second cleanup step, we still have 22% left. So this is sort of a semi-quantitative approach where you even don't need any Cal standards. You just can run it with your full scan data. Still, this is just one measurement for each sample, which I show here, on a generic method. So it's easily done. The whole analysis was done in 1 hour, and you can draw lots of data out of it. Okay, but to go on, if we are not sure what we want to see, or if we want to get one step further and be a little bit ahead of time and detect things we don't know yet, before it comes out somewhere in the supermarket, and something is in a sample which shouldn't be there, we go into unknown screening. How could you do that? We are still working with TraceFinder, and we are still taking, this is still the set of 4 samples. I'm still sitting on the same sample set, which I just used for this screening approach and semi-quantitative approach. I just now click a little button up here, which leads me into the software Sieve, which is installed on computer the same way. And then this pane opens here. If someone of you has come across Sieve, you will know the experiment setup in Sieve is quite complicated, takes you some time, and you need some knowledge of Sieve to get it done properly so the results are really doing what you want to do and you're not ending up with 50,000 hits of something you cannot even qualify at all. So this makes it much easier because the biggest part of this experiment setup in Sieve will be done by this little module we call Sieve plugin of TraceFinder. And there's just a number of parameters left you have to set. For example, for the framing, you have to set a couple of parameters. But then, once this wizard, and it's a 3-step wizard, is finished, Sieve will come up, fully parameterized. You just need to click it, and then Sieve will do its job. So the outcome in the end should something like that. Sieve is doing the alignment of the samples, so the retention time will be aligned, the intensity will be aligned, so the comparability of the samples is better. Then it will do the framing, so it extracts the components which might be in there by looking into every mass and looking if there is a peak or not. And then it will go into a predefined way of identifying these peaks. That can be an internet search on a database like ChemSpider. It can be just take a database which is offline on the computer, which you call dblookup. And this can contain as many components as you want. In this case, I just ran the same 2,900 components I used in the first example as well. And so this is what you come up with. So what's your job here? The job is now to find out what's significant. And that's the beauty of Sieve. Not this framing, that's quite nice, okay, but it doesn't get you where you want to get. The point in the end is do some filtering. So what can you filter on? This is this is a picture from that example. We are still in this wastewater treatment plant, and this is a comparison of what goes into the biological steps, so what goes into the wastewater treatment plant, and what's coming out of the first purification step. And then you see these are components which only go in but don't come out. These are components which are not going in but coming out, so transformation products. And this is what's more or less unchanged. Okay, for the wastewater treatment plant, I think that doesn't look too good. but basically it shows you what to filter on. It's the ratio of this comparison of these two samples. And now the question is, what do you want to look for? Do you want to look for the efficiency of your treatment plant? Then you will look into these guys up here, and you will filter for a ratio greater than whatever, 5 maybe, what may be significant. If you want to see what's coming out, what do I produce in my biological cleanup step? So what are the transformation products? Then you will look into these ones. You will filter for ratios which are smaller than 0.2, for example. Or you want to see, okay, which ones are the ones which are missed, where the wastewater treatment plant doesn't work properly. So you would filter for something around 1. If you look into the second step, the ozonation, you see, it looks much better already. So lots of components we really clear up. Lots of, not so many, but some we produce, of course. But still we have an amount going in. But that will be a different thing, of course. Many of these will be just background peaks, which are no contaminants, something like that. So that's the job of putting a label in the identification step later on onto these peaks. And basically, in the end, we can conclude that the vast majority of these peaks are not that the treatment plant doesn't work properly, but it's just background of the system. These are just peaks occurring. And in most cases, we can filter them out by intensity already, because the ones which are really of concern, they won't be with 1 E3 counts or something like that. They will be quite intense. Only if they are intense, they really have an effect. Another way to filter would be Pca analysis, which can be done in sieve. And just to show you what's the difference, this is a slightly different example, still surface water from the city of Berlin. And we have a couple of surface water samples. We have tap water as a control, and we have a control standard with some rather high concentrated components in there. Okay, what we see, a couple of samples have something in there. One obviously is completely different. That's the tap water. Makes sense. Here we have lots of contaminants in there. Here we don't, but it doesn't tell us a lot. But if we then again start to filter on significant changes of the surface water samples against the control, and I just put in a factor of 10. So everything which is 10-fold higher than in the control or 10-fold lower than in the control will occur here. And then we see, okay, here out of a sudden the control standard with the high concentrated standards in there is totally out of range. And here we have something funny, because this is the tap water, and these are the surface water samples. And now I can tell you the story behind it. This is a plant inside the city of Berlin, which is not meant to clean up contaminants, but to clean up the water of a lake called Tegeler See. They just want to precipitate proteins and nutrients for the algae and other organisms inside the lake, which make the water turbid and odorous as well. So they wanted to clean up that, and they do it by this treatment plant. And what's going in? These are 2 surface water streams. They are mixed in the plant, and then they come out of the plant. And what we see here, surface water 1 is a rather clear, pure stream. Surface water 2 is a rather dirty stream, because only 4 kilometers upstream is the biggest real wastewater treatment plant of Berlin. So all the efflux from this wastewater treatment plant goes into that stream. And then the fluxes are mixed. That's the intake of this precipitation plant and the efflux. And what we see here, that's the rather clean stream coming from the outskirts of Berlin, which is rather closely related to the tap water. It's clean. You more or less can drink it, obviously. This is the one which is coming out of the wastewater treatment plant. It's rather dirty. And here, these are the mixtures. And so this whole picture makes a lot of sense. Of course, we can say now, yes, easily to explain. We know what's behind it. But for me, it shows that such a Pca analysis makes a lot of sense. So what you can do with such a Pca analysis is just to look into series of samples, and you can see the outliers. You can see which are really closely related, because certain food comes out of the same region, or certain food has always the same quality, and then you have an outlier, and something's happening there. So that could be, for example, the indicator of a contamination. If you're thinking about pork meat or something like that, you have samples from the last, 2 years or so. You put together, you compare, and out of a sudden one is poking out. And then you can see, oh, Did one farmer feed a new antibiotic? Or what's happening here? Or is the meat just bad because it was not cooled properly? Things of that could happen. And that's what such a Pca analysis is really good for. And then you can start to go, for example, take one of the normal samples, which behave always, and the one which is an outlier to an A versus B analysis, and then start to filter again. And then you quite quickly will find out what's going on. And behind this, a very practical example from exactly the city of Berlin comes because they installed an Exacta system there, and they did exactly this one day when Sunday morning in a lake in Berlin, all the fish were swimming on the surface and were dead. So what was happened? Obviously, someone contaminated the water of that lake. And they quite quickly could put it down to a plant which was located at the shore of the lake. They really, during the night from Saturday to Sunday, they just opened a basin and just let the water flow out and contaminated the lake. And by doing such an analysis, they very quickly could find out what was the contaminant, so they could nail it down to that factory, and they immediately first could do the proper cleanup so the water didn't get into the water supply of the city of Berlin first. And second, they could sue the factory to pay for all that cleanup. And so it was a major win situation for them because during 24 hours they could say what it is, do the right things against it, and even could claim back the money for all the costs they had about that. Okay, and once you've done that, so you have done your done your framing, you have done your filtering to filter out what's significant for you, what answers a certain question you may have to these samples, and then you just put it back into Tracefinder. You just close the application, you say import results, and what's happening here, the filtered masses, which are somehow significant with their eventually already done identification, are coming back into Tracefinder, and they will go into a new database. And what you run in the end is just a second suspect screen inside Tracefinder just to do a quality check on these signals, because still it may happen that these signals don't have a proper chromatographic peak. You want to integrate it, you want to have a knowledge how much is it, and so on. And then you can go back and do all the things I did ahead of time already. You can do a semi-quantitative analysis, so you can follow up over a series. Is it the same? Does it somehow go down or whatever? And you can report it in the end. And so you get a nice whole package to run some suspect screens and unknown screen in one application on one quite simple data set. You can run in very short time. Okay, yeah, what you can see here, for example, isotopic pattern match, of course, comes again with it. All right, so that was a very quick spotlight on what we can do with Tracefinder. It's really just a couple of items taken out. Tracefinder can do much more, but it takes more than 20 minutes to show you that. So I put on some spotlights on some specific points, and I hope you get some interest in that. As I said, you can run the software on Orbitrap systems, on DFS systems, on all the systems we have inside Thermo. Okay. So I thank for your attention, and maybe you have some questions.